you who have taken on load all this work to organize it online. We didn't help here, so it's a big thank you towards everyone who is right now, I think, online and has been preparing and working on it.
Yeah. Well, we are used to working not just online, but as international teams.
Yes.
We are used
Hello.
to.
Good morning.
Good morning.
Good morning, Alexander. How are you?
I'm fine. How are you?
Good. I understand there are some problems with increasing COVID in Thessaloniki.
Yes, in Greece in total we had 125 cases, which is a record high. Yeah, they say that we will probably shift from level 3, go to level 4. Well, people are cautious. The people I see are cautious, but probably the young people who go out and drink a beer are not that cautious.
Yeah, and they carry, of course, it's not necessarily they who get ill, but people they are in contact with.
Yeah, absolutely, and the percentage of people who are hospitalized is relatively high compared to the number of cases in Greece.
Yes.
This is one of the alarming signals.
Yes. The other thing that we are suffering from in France is, you probably follow the recent terrorist attack.
Yeah, that was
and the relation between, France's tradition of freedom of speech and of freedom of joking about things and about religion and so on, which is unusual even in Europe. For instance, Greece, you can't make fun of the church or something like that openly, while in France you can make fun about everything, and it's part of the basic freedoms. And I think the events are showing a deep division in society.
It is really sad. And the thing is that everything that happens now in France or in Paris in particular is multiplied by a significance factor because of the history, the recent terrorist attacks. So it becomes even more frightening or alarming. Yeah, it's problematic because it's a matter of division in cultures.
Exactly. Deep cultural divisions. And I think that the position taken, personally, I think that the position taken by, for instance, Poland and Hungary, with respect to admitting people, is probably justified, because you cannot risk a whole society based on, it's great to help people to do good things and so on, but you have to evaluate what the impact is and whether you can manage it afterwards.
Yeah. What the attitude of your own people will be. If you expect that it will be a conflicting case, there you have to take measures. You're right on that.
The person who was the killer was a political refugee.
And a very young guy.
Young one, but his whole family was admitted to France based on political refuge from Russia. So
this is really sad.
Yeah. So it was someone who was subsidized by France, had looked after them for many years. So it's kind of shocking, and I think many of us think that really serious position must be taken on this, and we must change our course of action. I think the days of being naive are over.
After all, this is France, as you said. This freedom of speech is something more than a tradition.
Yes. Yeah, and
women.
Good morning, Dionysios.
Hello, good morning.
Hello.
Good morning.
I'm wondering whether our speakers are coming. Let's see who else is around.
Hi,
quite a few people are there. Hello, Pavel.
Hello, everybody. John-Louis is joining you.
Yes, hello. Hello, Tadek.
Hello, Errol.
Good morning. Thank you for you presented things very well. You added a few slides at the beginning, I think, to your presentation to explain.
Yes, I try to explain better what
That was very good. Thank you.
Subject.
Thank you.
Thank you.
Thank you very much. Yeah, I think that's we have a good problem there. We have a very good problem on this energy issue with respect to missions. I think that's on tient un bon problème.
Yes, yes. We are still working on it.
Yeah.
It's now Pavel who should expose the event. Maybe I look for him at his room.
No, Pavel is there, but I don't think I see his name here, but I don't think it's Pavel speaking. Let me just check.
Hello, can you hear me?
Yes.
Yes.
Hi.
Morning.
Hello, Pavel.
Hello, I had some problems with audio, I think.
I see. Are you sitting in the lab?
Yes, I'm sitting in my room right now.
In your office, yeah. Okay, let's look at what's the program anyway. Miltos?
Yes, hello.
Could you show the program so that we can start moving?
Yeah, sure. I will show the agenda.
Or I can show it if you prefer.
I can share my screen, it's okay.
Okay.
Just a minute. Can you see my screen?
I can see your screen.
Okay. So thank you for being here the second day of our symposium. It's also the last day of the symposium. Actually, today we have four presentations. We have two presentations at the beginning, then we will have a break at around 10:30 for about half an hour. And then we will have another two presentations, and then the concluding remarks by Errol Gelende. I think that we have all the presenters here. I'm not sure if Darius is here, but I saw that Paris Abgeriou is here. So I think we are ready to start, if you wish, with the presentations. So actually, each presenter will have 30 minutes, 25 minutes for the presentation, and 5 minutes will be left for some questions that may be posed by the participants. And I would like the presenters to respect this time frame so that we will stay on time. So the first presenter is George Digas. So just let me stop sharing my screen because I have some degradation issues. The performance of my laptop is reducing. So we have the first presenter is George Digas, who is a PhD student at the University of Groningen from Netherlands and also at the University of Macedonia, which is located in Greece. His research mainly focuses on mining open source software repositories and tracking the evolution of technical debt and the factors that incur it. So today she will present his work on calculating the technical debt interest generation risk, showing a case study. So now I will give the floor to George if he's ready.
Yep, I'm ready.
So probably you can start sharing your screen.
Sure. Okay, now I think you can see my screen, right?
Yes.
Okay, hello and good morning. My name is George Digas and I'm going to present our study on the risk of generate technical debt interest. This is a joint work between the University of Groningen and the University of Macedonia and has been conducted in the context of the SDK4D project and in particular on the technical debt toolbox. First of all, what is technical debt? Technical debt is a metaphor in software development that was introduced by Ward Cunningham in 1992. Basically, there are two ways to insert new functionality into a project. The first one is to design properly, which will take much longer now, but in the future, the things will be much easier if someone wants to maintain the project or to add new functionality. The second one is the so-called quick and dirty. This one it's much faster, but it might make the things much harder in the future because the quality of the produced code might be low. Doing the things with a quick and dirty way set up the project with technical debt. Like a financial debt, technical debt also incurs interest payments, which come with the extra effort that has to be spent in the future development. A software engineer can either continue pay the interest or pay down the principal by refactoring the bad code and improving the quality. This is a simplified schematic that we usually use in order to explain the concept of technical debt, namely principal and interest. If we assume that any given system has an actual state, it can be improved in order to brought closer to the optimal state, then the effort that is required to make that transition is called principal, as we can see here. The general assumption is that for a system that is not well designed, the actual maintenance effort is higher compared to the one that will be needed if the system were optimum. However, interest is also associated with the probability, because as we can see here, we will pay interest if and only if a new feature A or any other type of maintenance activity will be needed on that particular artifact. So interest has an inherent concept of interest probability. The probability of an artifact to generate interest is called technical debt interest probability. The generation of interest plays a crucial role for the impact of technical debt on the software maintenance. As this figure shows, if we have one artifact that rarely changes and it has low technical debt interest, then that artifact can be considered as an artifact with low risk. If we have a module that changes often with slightly higher technical debt interest, then that module can be considered as a module with medium risk. And finally, the modules that change frequently and have high technical debt interest are those that have the highest risk and can cause the real problems into a software. Thus, we consider the generation of interest as a risk that threatens the software maintainability. In this study, we propose a new metric which is called interest generation risk importance in order to estimate the risk of interest generation. According to Barry Boehm, the importance of a risk can be calculated as the product of the impact and the likelihood to occur. In the case of FIGRI, the likelihood of the risk corresponds to the interest probability, whereas the impact to the amount of technical debt interest. As I have already mentioned, this study has been conducted in the context of the SDK4D project. The main goal of the project is to minimize the cost, the development time, and the complexity of the embedded system software by providing tools for automatic optimization of multiple quality criteria such as technical debt, energy, dependability, and performance. Our work on the project was on the technical debt management and estimation, and moreover, we focus on the technical debt of new code introduced on each commit. Consider that software system evolved through a number of revisions. In each revision, several types of changes may occur simultaneously. For example, a class can be added, deleted, modified, renamed, or remain unchanged. The same also applies for the methods. In our study, we track the changes on the class level and we estimate the technical debt interest probability of the different component. As I have already explained, in this study we focus on the components that tend to change frequently. So the goal of this study is twofold. The first one is to assess whether the risk of interest can perform effective prioritization of technical debt items, and the second one is to examine the risk of interest generation posed by new code. The case study that we conducted is an embedded multi-case study in which the case is an existing software system which has been developed by Holsan, one of the partners of the project, and the units of analysis are the classes of that project. The analyzed project is a Java-based quality management system supporting the handling of business processes. It has approximately 100 classes, more than 150,000 lines of code, and has been developed for more than a decade. In the first step, we analyze the project source code using the SDK4D platform, and we quantify the risk of interest for every class of the project. Then we aggregate the results to the package level. And finally, we randomly selected 10 of the packages and asked the developers of the Holsan to rank these packages in terms of the maintainability risk. In other words, we asked them to assign the lowest value to the package that they believe has the lowest risk. The previous process led us to a dataset that is presented on this table. The first column has the name of the package, the second one, the interest per commit, the third one, the interest probability, and the final, the risk of interest. Based on the analysis that we performed, the highest risk are on the packages DB, models, and mail, because they have large interest and the same time significant interest probability. Another thing that I would like to mention here is that an interest probability of 1 means that that component changes on every revision, and accordingly, if the interest probability is 0.5, that means that the package changes on every other commit. So our first research question studies whether or not the risk of interest is able to perform an effective prioritization of technical debt items. As it can be observed from this figure, the ranking of the components based on the proposed metric is similar to the stakeholders' opinion on the risk of maintenance, and we can see it from the relative straight horizontal line. The majority of the deviations are relatively low. In most of the cases are by 1 rank, with only one exception, the package breeding, which it's ranked high according to the stakeholders and low according to our analysis. We can see that the package DB has been characterized as high risk both by proposed metric and the stakeholders, and the same applies for the package sorters, which has been characterized as low risk both by proposed metric and the stakeholders. The result based on the statistical analysis that we performed with the Spearman rank correlation are statistically significant, and the correlation coefficient was 0.82, which is relatively high. So we believe that this is a relatively efficient measure of risk interest importance. As I have already explained, we have a particular focus on the quality of the new code in this project. So the second research question studies whether the new code poses a low risk for generating technical debt interest. To this end, we compare the interest to the amount of new code and to the average quality of new code. In order to retrieve the required data and answer the second research question, on the first step, we retrieve all the commits for the project and we analyze them using the SDK4D platform. Then we map the identified technical debt issues to the methods. On the third step, we distinguish the methods that were newly inserted, and finally, we measure the contribution of new code to the project's quality using this equation, but I will not go into details. So the results of the first question of the first sub-question of the second research question can be, we can see them here. In this box plot, we can see the risk as it has been measured by the proposed metric. The horizontal axis classifies packages based on the percentage of new code that has been introduced. For example, the first bar corresponds to the package where 0 to 25% of the code that was introduced was new. And we can see the distribution of the risk interest. For the packages where they have high new code introduction, the risk of interest is significantly low and closer to zero. The results suggest that there is exists a very strong correlation coefficient with negative relation, and it is statistically significant. The negative sign of the on the relation suggests that the less new code is introduced in a package, the higher the risk is of the corresponding package to generate interest. The second sub-question of the research question 2 investigates the quality of new code and the risk of generating technical debt interest. Here, we split the package into two categories, where on the first category, we have the code that's a good quality, and on the second category, where the quality of the code was poor. Based on this box plot, it becomes evident that if the quality of new code is good, then the risk of generating technical debt interest is low. The interpretation of the results of our study are the following. The risk of interest captures with accuracy the urgency to fix the problems as that can be perceived by the engineers from Holsan, which is the company that we conducted the study. And the risk of code packages to generate interest is negatively associated to the amount, frequency, and extent of new code, which means that the cleaner the new code is, the less likely is to have interest in the future. We all know that prioritizing preventing maintenance tasks is a key activity in technical debt management, because usually tools yield thousands of suggestions, and the proposed risk of interest metric captures accurately the perspective of software engineers with respect to what has to be maintained. We also believe that the enforcement of the quality gates can decrease the risk of maintenance issues, and the quality gates can be easily added to a pipeline of a continuous integration system in order to check the newly committed code. Obviously, our study suffers from several threats, like the threats to code validity, because there are different issues in assessed technical debt. For example, we assessed only code technical debt, and we did not take into account the architectural technical debt. In order to mitigate the reliability threats, we provide a replication package for the paper. And obviously, there are significant threats to external validity because we used only one industrial project for our study. The conclusion of our study are the following. The proposed interest generation risk importance metric is a very simple yet efficient way to estimate the risk importance of technical debt. We partially validate the metric in industrial settings, and we argue clean new code lowers the risk to generate interest. Thank you for your attention. Any questions?
Thank you very much, George, for your interesting presentation. Your work seems to have practical importance in the field. So I would like now to ask if the participants have any questions to pose to you regarding the presentation. Okay, if no, I have some questions for you. First of all, the first one is just a justification, a clarification. I would like to know how you actually calculate the interest of the new code. Probably you mentioned somewhere, but I missed it.
Okay. Can you see the question on the bottom of the slide?
Oh, yes, yes.
No, okay. You mean the technical debt interest?
The interest, yes.
Okay. I don't have it. Okay. Give me 1 second. I have, okay. I have one backup slide. Let me.
Take your time.
So I think this one will help us to explain how I measure the interest of components. Let's say that we have an artifact under study like this one on the bottom left of the figure. This one has some properties like complexity, coupling, and cohesion, and that one has an optimum, hypothetical optimum state that can be brought. Based on that state, we measure how far it is from that state. Is it clear?
Yes, yes. So you check the difference from the optimal version of the same artifact, and then based on this, you calculate the interest, right?
Yeah.
Yeah, now it's clear. And I would also ask you, would like to ask you one general question. I mean, what is the bottom line of your work? Because it seems very promising. What would you suggest the developers to do? Because you found that when you provide new code, the risk of adding to the interest is lower. So based on your findings, is it better, would you suggest developers to actually, instead of doing refactoring, that it's better to rewrite some artifacts, especially when they are small?
Okay, I see. Actually, yes, I would like to suggest them instead of doing refactoring. So, okay, first of all, refactoring is a good thing to do on the code, but usually the developers avoid to perform refactoring activities because they think that is boring. They would like to focus on the new functionality. So I'm suggesting them instead of, if they don't want to perform the refactoring activity, then they should focus on the quality of new code and try to make it as good as possible. That one will help them to have a code base that is better quality in the future, and especially if we know that the old code usually after a few years it is deprecated and maybe it can be replaced from a library. We have another study which says that Google every year gets rid of about 20% of their old code and it's replaced by new library. So if they focus on the quality of new code and try to make it as good as possible, that one will prevent the system erosion. And also, and also, if they would like to use our proposed metric, as I said earlier, the software quality tools provide many suggestions. So to the one point that you don't know from which component you should start the refactoring activities. By using our EGRI metric, they can prioritize those refactorings.
Okay. And just a final, not question, but mainly regarding the future extension of an idea for an extension of the work. Is it, I mean, would it be meaningful to also include in the future, here you focus on technical debt interest, somehow to also combine the technical debt principle or something like this? It's useless, for example, or not meaningful.
Okay. In this study, actually, we also take into account the technical debt principle. Okay, I don't know how can I answer that.
Okay, I mean, just for the risk, I mean, if there's a point of calculating the risk of introduction of technical debt principle, yes, in the similar way, probably.
I think that the risk of technical debt principle cannot be applied.
Yes, yes, yes.
On this concept.
Okay, okay.
If I may help on that, Miltos, I think the work by Dimitris Tsoukalas and the colleagues at CERT who attempt to forecast the future evolution of principle of technical debt, this can be regarded as a sort of risk assessment, because once you establish that there is a high probability of having high principle in a future version, then you can probably take action.
Yeah. Thank you, Alex, for.
I also have a question, if I may.
Yes, yes, Darius.
Yes, please.
Yes, so George, it's not clear to me how you calculate interest. I mean, as far as I understood, the distance from the hypothetical optimal, isn't that the principal?
Okay.
Because I mean, the interest should be the extra effort you pay to, because you have not done the things the right way, right? And the
Exactly.
principal is the effort, is the amount of effort you need to fix the issue.
Yes, and in order to bring it to the hypothetical optimum state.
Exactly. So how are you using this information to calculate interest? And
If I may to help a bit, because this has been a big part of the SDK for a deep project. So principal is calculated based on the output of tools like SonarQube. So the assessment is based on the number of violations and the time required to fix them. For interest, as you said, this is related to the extra effort. So we use a proxy of interest. Interest is not something that can be quantified in a straightforward manner. But we use the proxy, which actually estimates the maintainability of a system. So we calculate the ratio of maintainability for a given artifact versus the maintainability of the hypothetical closest optimal. So this ratio gives you an estimate of how much effort, extra effort, would be needed, assuming a certain maintenance task.
Okay, thank you. That's clear.
Just a proxy. It's not an actual measure of interest, because ideally you would have to know how much effort would be needed for the optimal system, and obviously this is not available.
Okay, thank you.
Okay, thank you very much, George.
Thank you.
The others. If there are no other questions, we can move on to the next presentation.
I have a question, Jean-Louis speaking.
Yes, please.
Okay, so your goal is to predict the interest of a change based on current analysis of the artifact and their history. So I would like to know if you think about the idea of demonstrating a link or evaluating if there is a link between the risk level of a change and the technical density of the package into you want to make the change. Okay, so all the change are not all the same. If you change something in a very clean package, you introduce less interest or less technical debt than if you do the same change in the package which has a very bad quality, high level of technical debt, even if the change is the same. That's did you evaluate this idea, this potential relation?
So the question is, if someone changed something on a package that it's clean, and also if someone does similar change to a package that's not that so clean, if the...
I think that the level of technical debt introduced during the change won't be the same. That's like my personal feeling, and I would like to know if it is possible to demonstrate that by doing such kind of analysis on a real project. Then that will help you to predict, you know, the TD interest of a change. If you see the relation and you can say there is a factor which is this, then you can have a better model to predict. Okay.
Yeah. Once again, if I may help, I think that what Jean-Louis is stating is really interesting, there have been some studies that investigate the relation between interest and principal. Because you are right, for an artifact that suffers from a number of problems, it is highly probable that whenever you do a change, even the same kind of changes in another artifact, the probability of introducing more problems is higher.
Yeah.
This is right. Of course, we don't have the same measures for interest. I mean, we somehow quantify different aspects of quality with principal and interest for our own approach. We assume that for a system that suffers for several problems, its distance from the hypothetical optimal will be larger. So in this way, we would assess that the effort for the change or the impact of the change would also be higher. So not directly, but indirectly, we take that into account.
Okay.
You're certainly right that this is worth studying.
Okay.
How much worse when the existing code base is problematic? How much does it worsen the maintenance effort, the maintenance tasks? Yeah, you're right.
Also, to some extent, it lies in the heart of the definition of debt. So even in finance, the more principal you take, the more loan you take, the higher interest you produce, supposing that the interest rate is more or less similar. So the amount of interest is always, or it has to be related to the amount of principal. So anything different than that would be strange.
Okay, thank you very much for your questions. If there are no other questions, we can move on to the next presentation.
Thank you.
Okay, thank you, George. Thank you very much. So the next presenter is Darius Sas. Darius Sas is a PhD student at the University of Groningen under the supervision of Professor Paris Ethereum. His PhD project focuses on architectural technical data elimination in embedded systems with an emphasis on the evolution of architectural-related issues like architectural smells. Today, he will present his work entitled Exploring the Relation Between Code Changes and Architectural Smells. So I will give the floor to Darius now, if he's ready.
Hi, yes, trying to share my screen here. Okay, can you see it?
Yes.
Okay, so also now I believe it should work, right? Okay, so good morning, everyone. My name is Darius Sas, and today I'm going to present our work on exploring the relationship between architectural smells and code changes. So the goal for this study was basically to understand how reliability and maintainability, what's the interplay between these two qualities, which are design time quality and runtime quality. And we are going to do that by looking at two of their proxies. For reliability, we're going to use code changes. And for maintainability, we're going to use architectural smells. And we're gonna study these high-level qualities by looking at the relationship between these two proxies. We have identified three research questions for this study. The first research question was looks at the overlap between the code-changing artifacts and the smelly artifacts. So, for example, how many artifacts that co-change are also smelly and vice versa. For research question 2, we're going to do a statistical analysis, and we're going to look at how if co-changes are more likely to be found in smelly artifacts than in non-smelly artifacts. Finally, our last research question was to look at whether which one of these two phenomena occurs before the other one. So are smells introduced before code changes, or is the other way around? This is, for example, important to understand the understand the behavior of the phenomena that's succeeding the one that's preceding it. Okay, so what are architectural smells? So architectural smells, there are different kinds of architectural smells. The ones that we are considering in our study are the ones based on dependencies. So all these architectural smells are going to be based on the dependencies within the dependency network of the system. So for example, one class that depends on another one, or one package depending on another one. So for example, the negative effects that these smells have on the maintainability of the systems are, for example, for cycle dependency, is that they increase the complexity and coupling of the elements affected by the smells. And therefore, they lower maintainability, testability, and deployment. Obviously, if you have 3 elements in a cycle, if you want to test the unit test one, you'll have to execute also the code from the other one because they depend on each other. And the same is true for every one of the elements involved in the cycle. Moving on to the second type of smell, the hub-like dependency. This smell is, the structure of this smell is based as follows. So we have one central component, and this central component package or class has a lot of incoming dependencies and a lot of outgoing dependency. This, of course, means that this component centralizes logic and conceals actual dependencies of, for example, the components that depend upon it. So you don't know which one of the components that A depends upon actually provides the service that it delivers to the classes that depend upon it. Additionally, there is also, of course, the risk of increasing the change propagation chances, because if any of the classes on the left changes, then there is also a risk that the classes on the right change as well. And this, of course, will come and play when we also look at the code changes. The last type of smell that we considered in this study was unstable dependency. Now, this unstable dependency is very similar in the structure to hub-like dependencies, but here we only look at the outgoing dependencies. So, for example, if we have the central component A that has a lot of its dependencies that are less stable than itself, then we consider this A component to be an unstable dependency, to be affected by an unstable dependency smell. The negative effects of this smell is that the central component has an increased change, an increased chance to receive changes, and of course to propagate them to the components that depend upon it. Okay, so moving on to the code changes. So code changes are defined basically as 2 files, A and B. Very practical definition here. And these files, as they evolve and as there are multiple versions in the system, they receive changes.
Darius? I think we lost connection.
Disconnected, yeah.
Okay, I saw that he is connected. Darius, are you there? No. There must be a technical issue. Let's wait. Ah, he's here. He says in the chat. No. Let's wait a little bit. Probably he's reconnecting now.
Hello.
Hello, Darius.
Okay. I'm sorry. I don't know what happened. I had to restart Zoom. Okay. I'm trying to share my screen again.
Okay, please move on.
Okay. So let me go quickly to. Okay, so as I was saying, code changes can happen either in the same version, and in this case, it's easy to find them, it's easy to detect them. But the thing is that some files might also code change asynchronously. So one changes, for example, in version 2, and the other one then changes in the next version. So, and this pattern, of course, can repeat throughout the history of the system, and you need to be able to find a way to determine which code changes, which changes are can be considered code change and which cannot. Of course, the other type of change that you might have is an isolated one where only one of the file changes, and you don't want that to be considered a code change with the other file. So what are, for example, some of the drawbacks of code changes? So, of course, code changes can be considered as a manifestation of implicit dependencies. And one of the effects that this has on the system is that they expose the logical coupling between the two files. Logical coupling, of course, means that there is some kind of logical dependency between the two files, but it's not clearly manifested into the dependency network of the system. So the reason why we're using code changes as a proxy for reliability is that because they were also found to be predictors of faults. So if two files code change, it's very likely that they also that at some point in the future they will also start having faults. So this, of course, can be this is the reason we use code changes as a proxy for reliability. So detecting code changes is actually a very hard problem. There are different ways of detecting code changes because there is, of course, no mathematical definition of what a code change is, and therefore what exactly a code change is up to the implementation of the algorithm. So there are two main, there are several different algorithms that detect code changes. For example, the state of the art, a popular one used in the state of the art is dynamic time warping. This is a generic algorithm that that has several different applications from speech recognition to finance. And what it does is that it measures the similarity between two time series, and then it calculates the distance between these two time series. And if the distance is over a certain threshold, then those two files co-change. However, this approach does have some shortcomings. And we're trying to, we also developed our own solution, called fuzzy overlap. And through this solution, we try to, let's say, fix some of those shortcomings. So one of the shortcomings of this DTW algorithm was that it could not, for example, satisfy certain assumptions about code changes because DTW is a very generic algorithm. So fuzzy overlap through a series of formalizations, through a series of formalization of intuitive assumptions, heuristics, and intuitions, it tries to fix those issues. It does so by using 3 different thresholds, and and this also causes the algorithm to need configuration for every project it analyzes. So the way fuzzy overlap is working is very intuitive. The 3 thresholds that it uses are based either on time. For example, if you have a commit that's within a certain amount of 2 commits that are within a certain amount of time, we can consider them as the same change set, meaning that if two files change in the same change set, then we consider them a co-change. Alternatively, some commits are not within might not be within the time frame, but they might be consecutive commits. So let's say I commit one file today, and the next one I committed 3 days after the weekend, so it's over 24 hours, and then we're using commits. And finally, the last threshold is whether we have at least a certain amount of matches to ensure that the code changes we detect are not noise, are not just there by chance. Okay, so moving on to the case selection for our study. So we selected 14 open source Java projects, and we basically had a couple of different criteria when selecting these projects. We wanted to ensure that we had enough commits to ensure we were finding code changes, and we also wanted to ensure that we also found architectural smells. So we selected projects with at least 10K lines of code. These are the projects we analyze. As you can see, for some of the projects, we have a lot of change sets, which you can see something similar to commits. And you can also see that these projects vary in size by a lot. Okay, moving on to the first research question. So the first research question was about the overlap between code changes and architectural smells. And what we wanted to do here is basically to look at the start and end date of an architectural smell. So we found whether one of these two conditions hold. So, for example, whether the start and end date of the smell and code change were overlapping in any way possible. And during the history of the two files affected by the smell and code change. And if this was the case, we then consider that an overlap. Okay, so moving on to the results of the first research question. So here you can see the percentage of code changing file pairs that also happen to have to be affected both by the same smell. So in this case, you can see that a very high percentage of code changing file pairs are also affected by smells. And this is true for the vast majority of the projects. If we also want to take a look at the other side of the picture, we can also look at the percentage of smelly file pairs that code change. And in this case, we can see that we have much lower numbers in this case, because of course, an architectural smell might involve several different elements, whereas a code change is just 2 elements. So it's much easier for architectural smells to, let's say, affect a very big part of the system, and therefore fewer file pairs are found to be code changing. Okay, so moving on to the next research question. So the frequency of code changing in artifacts. So are smelly artifacts more likely to have code changes, or are in comparison with non-smelly ones? So what we did here was using a chi-square test for independence, which basically just counts the number of file pairs belonging to these 4 categories. And after doing that, we identified the null hypothesis, which is basically whether artifacts affected by architectural smells are as likely to code change as artifacts not affected by architectural smells. And to reject the null hypothesis, we're using 3 different criteria, which are the p-value, of course, the odds ratio, and the phi effect size. Since we are using 3 different criteria to reject the null hypothesis, we decided that it's better to not only have the usual rejection or acceptance of the null hypothesis, but also to have something in between, which is a partial rejection. And this was necessary because a lot of projects did not meet the third criteria by very little amounts. So this is the reason why we also have a third category. So if we look at the results, we have a full rejection for 50% of the projects, which is which is quite an interesting result. If we also look at the projects that were only partially rejected, we have just 4 projects, and in this case, we decided to, for example, the effect size only, as I said before, only achieved, for example, 0.9 instead of 0.10 of the threshold. So it meant it was making sense to put them in this category. And finally, we have 3 projects for which we have a full accepted null hypothesis, where there are no differences between the likelihood of smelly files and non-smelly files to co-change. So the bottom line for this research question is that we have solid evidence that suggests that smelly files are more likely to co-change than non-smelly files. The final research question looked at the order of appearance of co-changes and architectural smells. And in this case, to analyze this research question was just a matter of understanding for each file pair which phenomena appeared first. So we have, of course, 3 categories: co-changes first, architectural smells first, and simultaneous. The results show that in the vast majority of the projects, we have the co-changes that appear first, so before the smells. This is a very interesting finding, especially because the percentages are quite uniform across all the projects. We also performed some statistical tests to ensure that this is not just a graphical analysis, but we also use some statistical tools. So moving on to the takeaways of this study. So if we look at the global picture of a system, we have the file pairs, so every file pair in the system, and we have a certain percentage of those file pairs that are also smelly. And then we have the overlapping set of co-changes that stays, as we know, as we've seen from research question 1, that is more likely to be inside the smelly file pairs. So the major takeaway from this study is that smelly files allow co-changes to basically happen more likely where those smells are located. And this is interesting because the literature has also found evidence that this is the case also for cold smells and antipatterns. Which if we return to the initial goal of the study, we have that low maintainability affects reliability, because at all the different levels, we find that smelly file pairs allow for files to co-change more easily, and therefore introducing faults, as we know from the again literature who has studied the predictive using co-changes to predict faults. So moving on to the final takeaway. So in this case, we have a very interesting picture, because we can actually take a look, step back and look at the at how architectural smells are defined and introduced in the system. So the definition of an architectural smell is that it's an architectural decision, but when we analyze the system, we find actual structural dependencies that we do not want in the system. So how do we go from the architectural decision, that's the theoretical definition, to structural dependency? So one way this could happen is as following. So usually when you have an architectural decision, it follows that this is not 100%, it's not perfect. And this introduces logical coupling, because the entities defined in the architecture and the concerns are not clearly separated. Logical coupling, as we know, is basically another name for co-change. And co-change is, so when you have logical coupling, those two files are very likely to start co-changing. And as we know, co-changes precede architectural smells. So when two files start co-changing and they are not dependent upon each other, they might start also, since they co-change, they might introduce new code. New code means new dependencies, and new dependencies might introduce architectural smells. So now we have structural dependencies in the system, and these structural dependencies are even more likely to introduce co-changes. And again, this creates some sort of vicious cycle. And this vicious cycle, we believe that it's part of the bigger process of architectural erosion that every system undergoes through as it gets older and older. So this was my presentation. I wanted to thank you for your attention, and I want to mention also that this was, of course, a work that was part of the SDK4D project and was funded by the European Union Horizon 2020 program.
Thank you very much, Darius, for your interesting presentation, which is also the SDK4D project, as you actually investigate the similarities between two different quality attributes. Now I would like to ask the participants if they have any questions for you.
I'd like to ask the speaker, and perhaps also the other speakers who have worked on technical debt, how many papers have been published in this area by the project? Roughly about 10?
I'm not sure I can answer that question myself. I believe something like that, 10, 15 papers. I don't have the exact figure at hand.
Okay. So that's the order of magnitude. So it's not 1 or 2, it's about 10 papers, right?
Yes, I believe so, yeah.
So I was wondering, why are those not cited in your text?
We don't look at technical debt at a whole concept of technical debt, but rather what we are analyzing is architectural technical debt, which is a subtype of technical debt, whereas the whole other papers, the other members of the consortium work on different types, which are code or design technical debt. So this is one of the main reasons we do not have many citations from the project.
You mean they're irrelevant to your work? Is that it?
Not irrelevant, but I don't think they're enough relevant to be cited in our work.
Yeah, that's to me, it looks a bit bizarre. You're part of a project and you consider that the other work does not relate to yours, even though it treats the same subject. It's kind of strange to me. I mean, looking from the outside, of course, there are always detailed differences in details, and I've looked at this aspect, and you've looked at that aspect. But I'd expect a bit more a collegial approach when you write a paper in a project, that you are a bit better related to what other people are doing.
Well, the SDK
Kind
for
of
the
strange
project
to me that
is...
there is perhaps just 1 or 2 papers in the project outside of your own work that is worth citing.
So the SDK for the project is clearly mentioned in our paper, and we also state the points that are similar to our project, which are mainly trade-offs between reliability, between quality attributes. We also cite a couple of papers on that regard, and we believe there is no need to add unnecessary citations to a paper that already has around 30 or 35 citations. So yeah, that's the reason, but okay.
So you don't want to increase the citation of your colleagues' papers. I understand. Okay, very good. So fine. That was kind of my question, because looking at your written paper, it looks a bit bizarre. You know, in the project, there are so many papers on technical debt. And at the end
well,
of the,
to be honest,
it was like a collegial activity.
Well, to me, it looks...
Exchange of views and that you have been influenced by each other. Kind of.
To me, it looks a bit bizarre to ask other people to cite the papers if they're not relevant.
Your colleagues, it's part of the work of a team. So if you're saying we have not been influenced at all by all this other work, that's of course fine. Then you have no intellectual link to the other work. That I understand. If you say that, I can perfectly understand. But if you have been in meetings where you have been influenced by what other people say, and they have worked on similar or related topics, then you'd expect a bit more of a collegial activity.
I'm sorry, are there any questions that are specifically related to my work, or otherwise?
Well, this is related to your work.
I think we're wasting time.
No, we're not wasting time.
You are wasting my time.
Okay, I'm wasting your time. Fine. So I understand that your time is being wasted.
Yes, thanks.
Okay, probably it's time to have our break right now according to our agenda. Okay, this will also help us to relax. So I would suggest to stop now and get back at 12, as it's stated in our agenda. So if you are okay with this, we can pause our meeting now and just go and have some coffee and relax.
While?
Sorry, sorry, I checked the Greek time, sorry. So we will be back at 11 o'clock. Okay?
Yeah.
Thank you.
Thank you.
Thank you.
We got. Tak, tak. Znaczy w tej chwili się nic nie dzieje. Ale mam ściszony. Znaczy nie, w tej chwili jest wyłączone w ogóle. Nie,
Panie profesorze, Magda Sajdak z tej strony. Pan ma niewyciszony mikrofon, tylko informuję.
Hello. I would suggest to wait a couple of minutes for everyone to join, and then we could probably start again our session, the second part of our session. Okay? Okay, I think that we can start. I hope that you had the opportunity to rest during the break. So according to our agenda, the next presenter is Maria Mathiouthaki. She's a colleague of mine, so I know her very well. She's a research assistant at CERT. Her research interests include data science with emphasis on time series and machine learning forecasting. And currently, her research is targeted towards technical debt forecasting. Today, she will present her work entitled A Clustering Approach Towards Cross-Project Technical Debt Forecasting. So, Maria, if you're ready, I can give the floor to you.
Yes, Miltos, thank you very much for the introduction. Let me share my screen. Do you see my screen?
Yes, yes.
Okay. It's very nice to meet you all virtually under these circumstances. So, as Miltos said, my name is Maria Mathiouthaki from CERT. And today I will present to you our recent work, a clustering approach towards cross-project technical debt forecasting. Here is the outline of this presentation. First of all, I'm going to say a few things on the technical debt, and I will describe the purpose of this work. Then we'll give a detailed description on the experimental setup and the methodology that was followed. Afterwards, I will say what happened throughout our analysis and our results. And finally, I will conclude our results and say a few things on the future work we're planning to do. So basically, this work was part of the SDK for the platform, which generates forecasts for the three core quality attributes, which are the technical debt, the energy consumption, and the dependability. The current work focuses on the technical debt. Now, we're all familiar by now with the term technical debt, but let me just refresh our memory. It's a term that has been inspired by the financial economic theory, and it basically describes the problem of making quality compromises that can yield short-term benefits, but may negatively affect the long-term quality of software products. Now, predicting the evolution of the technical debt is of paramount importance, as it can significantly contribute to decision-making support and estimating the point to which the software product could become unmaintainable. Now, in our previous work, we have employed statistical time series, machine learning, and causal models to generate forecasts for the technical debt. However, all these approaches assume that there is historical data sufficient enough to have a proper training process. But what happens if there is not sufficient data from a project? In this case, cross-project technical debt forecasting concept offers a possible solution. We propose a clustering-based approach that aims to improve the performance of cross-project technical debt forecasting models. And having said all that, we have come up with the following research question, which is, can data clustering improve the accuracy of cross-project technical debt forecasting? Now, moving on to our experimental setup and methodology. Here we have a visualization of the overall approach that we followed throughout our work. There are four main steps. The first step consists of the definition of the data and the preparation. So the definition of the data takes place as the source code of multiple software projects is retrieved from code repository along with their history. We applied a static analysis provided by SonarCube on these projects in order to obtain the technical debt indicators per project. We have some data preparation just before step 2, which is basically the clustering of the projects. We assign the projects into groups depending on their characteristics, such as their complexity, their size, code smells, bugs. And step 3 consists of the construction of the kernel models. So we construct a representative kernel model for each of the clusters that we have. And then during our final step, when a new project arrives, we again perform a static analysis in order to obtain the technical debt indicators. We assign this new project to one of the already existing clusters, and we use the dedicated model of that cluster in order to generate forecasts for the technical debt principle. Now, more details on every step will be given right now. First of all, the data collection. We have 30 real-world open source Java projects retrieved from the Apache Software Foundation that were obtained by Lenarducci's paper. 27 of these projects were used throughout the clustering and training process, and the 3 remaining projects were used at the end of this work as case studies. For each project commit, static code analysis was performed using SonarCube in order to extract the technical debt indicators as our independent variables and the technical debt principle as our dependent variable, the variable that we want to predict. Now, the technical debt principle is the effort to fix all code violations, code smells, bugs, and vulnerabilities expressed in minutes. So let's move on. Now we have the data preparation. Data preparation basically consists of 2 steps. The first one was the feature selection. We applied 4 different feature selection algorithms in order to identify which of the technical debt indicators are statistically significant for predicting the technical debt principle. And they were namely code smells, bugs, vulnerabilities, complexity, and NC lock. And then we applied a method called the sliding window, which is a method that allows for the model, rather than taking under consideration only the current commit, to be able to take under consideration the past few commits, the past few steps of the dataset. Next, we have the project clustering. We use the k-means clustering algorithm in order to assign our 27 projects into groups. We can see here how these groups are formed on the left hand table. And the number of the clusters is indicated by the elbow method. It's 6. And on the right-hand side, we can see we have reduced the dimensions to just 2. We have on the y-axis the technical depth, and on the x-axis we have NC-log, which is the lines of code. It's a randomly selected variable out of the statistically significant TD indicators, just to visualize how these groups are formed. We move on to step 3, which is the construction of the forecasting models, which are the representative models of each cluster. We examined 5 different algorithms. 3 of them were linear, and these were linear lasso and ridge regression, and 2 of them were non-linear, and they were SPR using the Gaussian kernel and random forest regression. Experiments were performed for 5 and 10 steps ahead, and mean absolute percentage error was used for the model evaluation. Now, after the construction of the 6 representative models, we assigned the three data sets that I stated to be the case studies. We assigned them to clusters. So Commons Jelly, Commons Codec, and Commons Diputils were assigned to cluster 2, 3, and 4 respectively. There is one key question that we want to answer at the end of this work. Do the kernel models of the clusters that the datasets have been assigned to produce better results, better predictions than the dedicated kernel models of the rest of the clusters? Now moving on to the analysis. The purpose of the first step is to validate whether or not cross-project within cluster predictions are better than cross-project cross-cluster predictions. What this means is that if we take 2 data sets belonging to the same cluster and we train the model on one and test the model on the other one, are the results better than taking one data set of one cluster, train the model on that data set, and then test it on a data set of a completely different cluster? To answer this question, we take every single data set of the 27 data sets, train the model on that data set, and then test it on the 26 remaining data sets. In this way, we obtain 702 performance values for each of the algorithms. And here we can see a fragment of the performance values when lasso regression was used. We can even see that next to each data set, there is a number indicating the cluster that this specific data set has been assigned to. And if you want, you can see our supporting material online if you want to see the 5 tables with all the values that we obtained. Just by examining these 5 values, these 5 tables, we can say that the performance values tend to be lower in within forecasting rather than cross-cluster forecasting. However, in order to be certain that there is a significant difference between these two, we applied the Wilcoxon's rank sum test. And here we can see the results, and we can definitely state now that there is statistical significance at the level of 95% confidence interval, as all p-values for all algorithms were found to be lower than 0.05. As our next step, we focus on within cluster performance values, as we want now to generate the representative kernel models per cluster. This has to be identified not only on the forecasting algorithm that we will use, but also which of the data sets of each cluster is better to use as training data set. Here we can see an example. This is a table representing the performance values of cluster 0 when lasso regression was used for 5 steps ahead. And we can see that the last row consists of the mean values of the performance values that were obtained when a specific data set of cluster 0 was used for training. And the bottom right cell is basically the mean value of all these values, which represents the performance of this specific algorithm on this specific cluster. Now, these results were obtained for all the clusters, for all algorithms. And in order to visualize the results, we put them on graphs. On this slide, we can see an example of these graphs. This is specifically for cluster 0 for 5 steps ahead. We can see the performance of all the algorithms, and we can see, for example, that SVR gave us the worst results, whereas linear lasso and ridge regression gave us the best results, especially here, especially when HTTP components client and commons configuration were used as training datasets. Okay, so by inspecting all these graphs, we are now able to see, to state which of the training datasets are optimal for each cluster, and also which of the algorithms was optimal for each cluster. And the point is now that when a new dataset arrives and we want to generate forecasts for, it's very difficult to find a pre-trained model that is suitable for this new dataset. So what we chose to do for more generalizability is that we chose to merge the 30% of the total number of data sets of each cluster, the best performing 30%. We merged this data set to use as training data set of that specific cluster. So having now ready our kernel models, we move on to our case studies. As I said at the beginning, we have 3 case studies, 3 data sets retrieved from the same paper. We see here the results for these data sets, and we can clearly see that indeed the pre-trained kernel models of each of clusters 2, 3, and 4 produce errors lower or equal for each of the new testing projects compared to the pre-trained models of other clusters. Now our conclusions and future work. It's very clear to us that the adoption of clustering is a promising solution for enhancing the accuracy of cross-project technical depth forecasting. We saw that indeed, if we take under consideration the similarities of different projects, we can assign them to groups, and within clustering forecasting is indeed much better, gives us way better results than cross-cluster forecasting. And we were able to evaluate successfully these results using 3 previously unknown applications. As our future work, we aim to investigate the generalizability of our approach. We want to test it on projects that are retrieved from different domains, written in different programming languages. We're looking at C, C++, and Python. And we want to investigate the extension of cross-project technical depth forecasting to lower levels of granularity, such as package, class, or function level. And we want to also investigate the performance of perhaps more sophisticated clustering algorithms, such as hierarchical clustering or the agglomerative clustering. So I think, yes, that was basically it. And if there are any questions, would be happy to answer.
Thank you very much, Maria, for your interesting presentation. Sorry, Errol, are you speaking?
I had a question, Mr. Chair. May I ask it?
Okay.
Yeah, this is very interesting because clusters allow you to discover, of course, you're clustering projects or your clustering software, but behind this, there are hidden things that typically come out in clusters. For instance, earlier in the discussion with Darius Das, we discussed, he said, well, we're looking at architecture. Well, typically what you discover is similarities in architecture, for instance, when you cluster. So this is, I think, a very interesting way to look at higher level properties of software units or components or systems. And I was wondering whether you had discovered something like that, or whether you're still at a preliminary stage where you're just exercising the clustering algorithms to find out whether they work, they don't work, etc., etc.
Yes, currently we're at the early stage of this approach. As a matter of fact, we use SonarCube to extract the technical depth indicators, and we just receive these technical depth indicators and we generate forecasts. So there is not a big research on what these indicators might be as to the architecture and how important and how crucial they are. So this is something, it's very interesting, and of course it would be something we're looking to understand and gain a better insight. But at this point, we just look at them as variables, as indicators for the technical depth, at least for now.
Yeah. So perhaps some interesting interactions might occur if you could get, for instance, examples with different architectural structures, or perhaps in different areas like numerical programs or say optimization programs or whatever. I mean, there may be some interesting commonalities that then lead to clustering.
Yes, this is something we want to investigate further, because as I said, these were data sets retrieved from one single paper. They were all applications written on Java, and they represent a specific, they're from one domain. Yeah. So we do want to investigate this, yes, further.
Of course, languages may also influence, as you pointed out. The programming language itself might influence the clusters.
Yes, of course.
Thank you very much for this interesting suggestion. Actually, it gives ideas for additional work in the future and the new directions for this paper. I would also like to ask if there are any other questions from the other participants. Okay, actually, I have a more technical question based on the presentation. I would like to ask you, because you said about historical data, what is actually considered a sufficient amount of the data to share?
Yes, this question is crucial indeed, but there is not a clear answer as to which kind of data is considered sufficient or not. So how short is the data set? How short should the data set be so that we can apply this approach? This is not an answer we can currently answer. We can totally state, though, that data sets that have an evolution of a technical depth that has a clear trend, so it's easier for the model to catch the trend of the technical depth. This is an approach that, it doesn't have to be large to let me rephrase. So when you can easily forecast the technical depth because there is a clear trend, this is a sufficient data set. Whenever the patterns of the technical depth are not as clear, and the data set is also very short, so the model cannot do the training. The training should be done in a bigger data set. Then we believe that this approach is better. In practice, we would suggest that when someone wants to generate forecasts for a data set that is not sure whether it's sufficient history or it's not, they should try both a traditional model training and also this clustering approach and see whether the results are better.
Yeah, so or probably there's not a sufficient amount of data in the beginning, probably the process is new. As far as I can see, probably you start with this approach, you reuse a model that was pre-trained with a similar application that has similar functionalities, and then probably do retraining or when the data are available to probably add this data to the data center during training or something like that.
Exactly.
I see also this direction as well. And finally, I would also like to ask you how if you're planning to implement this interesting approach in the SDK for the project.
Indeed, we're looking to implement these new findings in the SDK for AD platform. Of course, we all know that the SDK for AD platform is at the state of the finalization right now. So we need to act fast, but indeed we will implement these results. We will try to implement these results to the SDK for AD platform.
Okay, that sounds great. So are there any questions, other questions from the panelists? Okay, then we can move on to the final presentation of today's session. Actually, the final presenter is Katarzyna Pilus. She works in the Computer System Modeling and Performance Evaluation Group of the Institute of Theoretical and Applied Informatics of the Polish Academy of Sciences. She is also approaching the completion of her master's degree at the University of Technology. Her main area of research is machine learning, especially neural networks. Her current scientific interests are also network and software security, network traffic analysis, and autonomous vehicle positioning. So today she will present her work on software vulnerability prediction using random neural networks. So Katarzyna, if you're available, I can give the floor to you.
I hope you can see my presentation on the screen. Do you see it?
Yes, we can see it.
Okay, thank you. So good morning, ladies and gentlemen. I am glad that I can discuss the topic of my presentation today, and it is software vulnerability prediction with random neural network. And in this work, we examine the effectiveness of applying mixed features, describing software elements, and a model based on convolutional neural networks and random neural networks in the task of vulnerability prediction. It is one of the many approaches on how to improve the security of the software. And it is, I think, one of the hottest research areas nowadays. Both the scientific and the business world aim to provide better and better solutions. And this work has been conducted in the context of the SDK for ED project, particularly the dependability toolbox. And now I would like to tell you a little bit about the agenda of today's presentation. So first, I will tell you a little bit about the meaning of software security, as this is the topic of presentation. Then I will introduce the term of software vulnerability. The next step is that I will tell you some methods that are used to enhance the security of applications. Then we will go to software vulnerability prediction itself. And I will divide the analysis, methods of analysis into two groups, static and dynamic analysis. Then I will focus on static analysis for vulnerability prediction. And I will introduce the model of random neural networks. And then we will go to methodology, experimental results of the work, and at the end, some conclusions and future work. So first things first. Now I would like to tell you a little bit about software security and the meaning of software security. So in the Cisco annual report 2019, the security was named foundational and the top IT priority. And in their other report, Cisco Consumer Privacy Study, also from 2019, 84% of respondents told that they cared about the data privacy, about the security, because of course it is all connected. but only 48% of respondents told that they did take any action to improve security of their applications. In other report, State of Software Security Volume 9 from Veracode from 2018, it was indicated that more than 85% of all applications checked with the software contained at least one vulnerability in them, and 13% contained one critical security issue. So as we can clearly see, security is important for people, privacy is important for people, but a lot has to be done in this area. So now, very important thing. I think we all know that applications are based on source code, but it is very important to realize that if the basic component of software is source code, it is vital for it to be written in a proper manner, which focuses on the security issues. So what if the code includes some defects? Now I would like to introduce the term of software vulnerability. So it is a subgroup of software defects, which are the parts of code written in the wrong manner, we can say, that introduces the danger to the security of the application. So now, in other words, let's just think about a very simple, well-known attack, SQL injection. So, of course, the responsibility lies on the attacker's side because they conduct the attack. But software vulnerabilities, in here, they can be named as, for example, that the data supplied by the user is not validated, filtered, or sanitized. So this creates a doorway for the attacker, and it could have been created. It could have been prevented, you know. And usually, software vulnerabilities are caused by common programming mistakes, and they are introduced by the programmers in the early stages of the software development lifecycle. And they are usually caused by the lack of security expertise of the programmers and also by the limited testing resources. Now I would like to present some methods on how to enhance the software security. So firstly, even the modern programming languages themselves, they focus on safety and reliability of software, and they want to enhance it. And for example, in the first group, which are the languages OCaml, Java, and C#, these languages utilize static analysis and dynamic checks to improve the security. Of course, nothing is perfect. Nothing is completely secure, but it's just trying to improve it. And we've got a new generation, we can say, of languages. And the example is Rust language. This language is recommended for the safety critical domains. And it assumes memory safety and thread safety. Additionally, we've got organizations, software-oriented, security-oriented organizations like OWASP or SANS Institute, and they create standards. For example, OWASP Top 10, CWE SANS 25. These are the lists of well-known vulnerabilities. And also they create guidelines for programmers on how to create better and more secure software. And here we can mention OWASP Secure Coding Practices Guides. Also programmers can use static analysis tests in the coding stage of software development lifecycle, directly in the IDEs or using some plugins. And for example, for C, C++, they can use Visual Studio. For Java, they can use the IntelliJ and Eclipse environments. But also, they can use some dedicated tools. And the examples are SonarQube and Veracode. Okay, so now we can move on to software vulnerability detection and prediction. Okay, so we can divide this area into two groups, static analysis and dynamic analysis. Static analysis can be introduced in early stages of the software development lifecycle. So this is a huge advantage of this method. It is usually based on text mining, software metrics, or security-related automatic static analysis alerts, in different words, ASA alerts. And it works well in detection of leaks of private data, unauthorized access to resources, permission misuse, intent injection, and code verification. The other group, dynamic analysis, it is also very useful, and it should be used in the process of creating a secure software, but it is more time consuming. So it is a big flaw. It can be executed only if we have an executable version of the product. And that is why it can be used later in the software development lifecycle. And some examples are fuzzy testing, concolic testing, and search-based testing. Okay, so now I would like to focus on the first group, static analysis-based vulnerability prediction. So as I mentioned before, it is usually based on these three groups of features. So we've got software metrics, and the examples are complexity metrics, CCC, which is complexity, coupling, and cohesion, code churn, and for example, developer activity metrics. The second group is ASA alerts, and we can obtain this feature using some static analyzers. And the last group is text mining based features. And this approach is very similar to natural processing, because, for example, we can use a technique called bag of words, and it uses tokens with some associated frequencies. And this is the representation of the code. We can also use a technique called n-grams, in which we treat a few words as one word, we can say, in a bag of words. We can also use some more program-based, we can say, approaches. For example, as features, we can use includes and function calls. And also, the code itself can be represented on different levels. For example, we've got high level or low level. And for low level, the example can be, for Java, can be Java bytecode. But in here, it can be a little bit risky to name Java bytecode as a low level representation, because it's just a lower level representation, because these are the instructions for the Java virtual machine, not the processor, like it is for executable files in C++. So it's just a lower level, we can say. We can also mix these features, and some works compare the results achieved using different methods, but these results are often contradictory. So I think they can be biased by the data used, projects under consideration. Many different prediction models, because now we know about the features we can use, but prediction models. These are some standard machine learning models, but most popular ones in this area are random forests and deep learning approaches, artificial neural networks, at least from my research. Okay, now we can focus on the model of random neural networks. So they have been introduced by Professor Errol Gelenbe. In such a network, positive and negative signals circulate. We can describe a neuron using its potential, its natural number. And if this value of potential is greater than 0, a neuron can send a signal, positive or negative, to another neuron or to the outside of the network. Positive signals are responsible for excitation and negative for inhibition. And excitation means that it increases the neuron's potential, and inhibition that it decreases this value. The structure of a random neural network can be feed-forward or recurrent. And in this particular work, we allow all the connections between the neurons besides the connection from a neuron to itself. Why we use RNNs in our work? So RNNs exhibit a great classification power and are able to outperform other traditional methods in many, many different areas. And some examples of areas in which RNNs were very successful are, for example, vehicle classification, medical image segmentation, also the fields of virtual and augmented reality, and attack detection. In our work, we use a special weight restriction that minimizes the number of computationally demanding operations by considering only the derivatives of positive weights during the gradient descent optimization algorithm. So it makes every step of the optimization algorithm faster. We also initialize the network in the way that it can be perceived neutral at the beginning, which is very important for a classification task, because this way our network isn't biased at the beginning to any other option, to any of the options. Okay, so now the methodology. We use text mining features and metrics obtained from a static code analyzer, namely SonarQube. We chose 5 best features from static code analyzer using chi-squared ranking technique. We also use 2 models of neural networks, convolutional neural networks for text processing, text mining features, of course, and a random neural network as a bonding model, as a final classifier. And we use a standard machine learning procedure, and we divide our data set into 70% for training and 30% for testing. And we also use T-distributed stochastic neighbor embedding, which is TSNE algorithm. Maybe this name is a little bit is better known. And it can be used to examine if a local structure in high-dimensional data exists, and it allows us to visualize it in, for example, a 2-dimensional space. So we can easily observe if this local structure exists. So when it comes to data set, we use a data set which is a code base and associated labels introduced in the following article. In this article, they also introduced their own deep learning based system for vulnerability detection. It was called ValDePecker. And the code base contains C, C++ files and 2 types of vulnerabilities, CWE119, which are buffer error vulnerabilities, and CWE399, which are resource management error vulnerabilities. And in this particular work, we focused only on the second group, CWE399. For text processing, we used a technique called bag of words, which is tokens and associated frequencies. And this approach was used in the following article by Scandariato et al. And we used metrics obtained from a static code analyzer, SonarQube. And on the right, you can observe the number of instances in both classes and in total. Okay, so I think we can go further. So here you can see the proposed system. I think it's easier to use the graphical information. So we can divide it into 2 groups, we can say. The first group is text processing, text mining based model. So we've got source code files. We represent them using tokens with frequencies, reshape it and give it to CNN. And from CNN, of course, we can have information itself, classification, but we can also use feature maps generated by one of the layers. Using this technique, the data is processed and the dimensionality is much smaller, so this is great for us. And the second group is based on random neural network. It is called the bonding model, we can say. So in this part, we connect software metrics, 5 best software metrics obtained using SonarQube, and of course the same files as for text analysis. And we connect them with these feature maps we obtained from CNN. And RNN here is a bonding model. And using the fact that it is a great classifier, we chose to use this particular neural network to give us a decision if a file is vulnerable or not. Okay, and now the experimental results for the best model. So we achieved 97% training accuracy for both text mining based model, this is this first part, and for the hybrid model, which is bonding model, we can say in other words. On the right, I decided to present the confusion matrices because they give us, can say, the full knowledge about the accuracy and the performance of our neural network. And for testing, the accuracy was a little bit lower, but still very good, I think. So it was 93% for a text mining based model and 94% for the hybrid model. So we can see that the generalization of the model is still very good. And the other thing we can perceive, it is that specificity, which is true negative rate, in other words, of the hybrid model is better in testing a case. And it means that less examples are mistakenly labeled as vulnerable instances. Now I would like to present you the results obtained, graphical results obtained using the TSNE algorithm. So as we can clearly see, the local structure is visible in all of the instances. It is a little bit less visible for static analysis metrics obtained from a static code analyzer, but still we can observe this local structure. So the data has some potential to be used in classification. And using both features allows us to achieve almost a linear separation in the grouping task. You can see it in the picture below. Okay, and now conclusions and feature work. The analysis performed using the TSNE algorithm proved that the high-dimensional features we use for training the models contain a local structure and can be used in the task of vulnerability prediction. This structure is less visible for the static analysis metrics, but they still have the potential to be used in the vulnerability prediction models. The biggest problem of most vulnerability prediction models and static analysis tools is a significant number of false positives. And our experiment displays that using both text features and metrics generated by a static code analyzer can reduce this number slightly. However, to fully evaluate the proposed method, more tests with existing models should be performed, and maybe more complex neural networks should be used because they can give us some better results. And such models should be tested on bigger data sets containing maybe different types of vulnerabilities, maybe different programming languages. I mean, codes written in different programming languages. And for our future work, we plan to build a general vulnerability prediction model that tells us if a program is vulnerable or not. Or as an alternative, we can build a bigger system with multiple classifiers, multiple models considering different types of vulnerabilities. So these are the plans, and we also want to focus on more exhaustive statistical feature analysis and selection, especially in terms of features generated by a static code analyzer. Also, maybe using different analyzers would be a good idea. Okay, so that is all. Thank you very much for your attention. Do you have any questions?
I have perhaps a question. This is Errol.
Okay.
Thank you very much, Kasia, for the excellent presentation. I was wondering, have you been able to randomize the test and well, the learning and testing data? Have you been able to randomize it and run it on multiple versions, or is this based on just one selection?
It was the best model. I was randomizing in the data set. the numbering, the order of the samples, but this is the best model. But they were quite fine. You know, it's just a preliminary work, and that is why.
The randomization. And the other thing is, you know, what happens? You have 70-30, but real life is. Real life, of course, is the training data sets are much smaller than all the applications that the system encounters. Suppose we have a smaller training set and a bigger testing set. What happens? Is there a lot of dispersion of the results, or is it?
For future work, we can try to do this, but you know, the advantage of using a bigger data set for training is that we have a chance that our model will be more accurate because it sees more samples. So
no, that's
this is a standard.
Of course. But that's the real world is where we have little training data and a lot of testing data, because once you've trained the system, you let it run for a long time. And so it encounters a lot of variation. So somehow, you're right. I mean, of course, if we have a bigger training set, we're better off.
Just for future, we should try a bigger data set, I think.
Sure. Thank you.
Thank you.
Thank you, Katarzyna, for your presentation. I would like to ask the participants if they have any questions. Okay, then I would like to ask you a couple of questions.
Of course.
First of all, thank you for the interesting presentation. And actually, to the best of my knowledge, since I'm aware of the field, this is the first time that random neural networks are used. And they have demonstrated, at least at this preliminary work, very promising results.
Yeah,
so
they have a potential.
Yes, and also we were discussing, and you said now that probably you will use a bigger data set. Another idea would be, if we manage to find a bigger data set, if it would be a good idea to also use, to try deep learning with random neural networks, because actually recently it has demonstrated very promising results in different fields. So probably it will demonstrate also here in vulnerability prediction. So what do you think about it?
Maybe we can try it in the future. For now, I decided to use convolutional neural networks for text processing because it is the most demanding part, and it gives me a huge dimensionality reduction, and that is why I used this one for this part. But maybe random neural networks will work with text mining data too. But it needs a lot of work to be done, of course. Sure. But as a bonding model, I think it works very well, and we can expand this solution.
Yes.
It's that the CNN has a lot of existing software.
Yeah, exactly. And it is very well optimized.
Everything from the beginning is a lot of work. That's what Kaja is saying.
Okay.
But perhaps we can get some of the software from one of my former students.
Yeah, it would be great. I would like to test more.
Who actually designed RNN-based deep learning algorithms, and we published quite a bit of that. Yeah.
If they would like to give us the code, it would be great.
That on character recognition and so on. So, yeah.
Okay.
So I'm waiting for the code.
Yeah, I know.
Okay, and one final question. You said that in the future work you're planning to examine data from different study code analyzer. Why is that?
You know, in data science, generally, it is a good idea to try different approaches, also data from different sources, because it can give us some wider information and maybe complementary information and make our model more accurate, better.
Yes, indeed. Okay, I think I'm covered. Are there any questions from the participants? Okay, then thank you, Katarzyna, for your presentation.
Thank you. Thank you for having me.
And actually, this was the final presentation of the day session, and actually the final presentation of our symposium. And I would like to thank all the presenters and the participants together here. And actually, now we have the closing remarks, the concluding remarks, which will be given by Errol. So,
and Magdalena, perhaps, yes. So what would you like to say, Magda?
Well, I would like to thank once again for all the presentations as well, because it has been outstanding work done by all of you. So thank you very much. Thank you very much for participating in this conference, because obviously it might, it's fantastic that you have given us your time and participated and shared your knowledge. So thank you for this. And thank you very much to the organizers, to Ariel especially, and to Professor Czachurski for, and the other side, all this, all the team that has actually made this possible today, because it wasn't us that has made this possible. It was you who made it possible. So I would like to say thank you for that.
Thank you very much, Magda, for your support and your enthusiasm, with which we would not have started. If we hadn't met it initially, it would not have happened at all. So thank you. And thank you also, Tadek, for your support and enthusiasm. Thank you, Dionysios, for also accepting the proposal, because if you had said no, we would not have done it either. So that's important, very important. Thank you, Maria Jankovic, and Miltos Vitiadis Siavas, for your active support, all the speakers for your help and participation. Without the speaker, we wouldn't have had anything. I'd also like to thank offline SN Springer Nature Computer Science, who have accepted to produce a special issue or a group of papers appearing together. So the papers are nearly ready, I think, very close to being ready. So we will soon forward them. They will pass through the formal checks that are preliminary to, if you wish, copyright collection, because papers have to be unpublished in a certain sense. So we can't have more than a certain percentage of duplication with other papers, but there will be just a formal check of that. And then the papers, we have them. I have 4 in final version and 1 not quite finished yet, but Mitos will send it to me. So we will send them up, and of course we will recognize all the organizations that have participated in this, including the Scientific Center of the Polish Academy of Sciences in Paris, and IITIS, and SDK4ED, and and I'd like just to mention one more person who hasn't appeared at all in this picture, Krzysztof Groszla, who has been extremely kind in supporting us and helping us set up web pages and so on. This is a non-trivial but extremely useful help. I'd like to say a big thank you to him, even though he is absent from this meeting. I think we've had a very enjoyable and interesting, dense program, quite varied, with different ideas coming into the picture. And I think the project is not quite over, SDK4ED, and I'm sure we'll have other very interesting things happening, technical things happening in this project, and human things as well. Well, my then thanks and greetings to all of you, and hoping that we have a good end of week and a nice weekend with a bit of sun perhaps in Thessaloniki and elsewhere. See you soon. Bye-bye.
Thank you so much.
Thank you very much.
Thank you very much. Bye, everybody.
Thank you. Bye.
Goodbye.
Thank you. Bye.
Bye.
We still have good weather in Thessaloniki. Hopefully it will remain so.
Yes. Sign a contract with the Weather Bureau.
Yeah, that's a good idea.
I'm looking forward to
again, I take
event like this. Sorry, Magda.
No, sorry. I just wanted to, now that most of the participants are gone, I wanted to say very much thank you for organizing it online. It has worked fantastically, and thank you for all the effort from everyone once again. It has been really, really a pleasure to cooperate and actually to see this work fantastically with the Zoom. It's a good experience.
Thank you very much for hosting us.
Let's do it again.
Yeah, let's do it again, perhaps live.
Next time